Welcome back to the Deep Dive. Today we are opening up the hood on one of the most critical quality attributes that secretly dictates whether your software project runs smoothly and affordably or, well, spirals into massive maintenance costs. Testability in software architecture. We're diving into a stack of source material focused specifically on how architecture actively facilitates testing. We'll start with some wisdom from the aerospace world, actually, from Burt Rutan. Testing leads to failure, and failure leads to understanding. Our mission today is understanding how we design systems so they fail quickly and cheaply, ideally right from the architect's drawing board.
That sentiment, yeah, it perfectly captures the goal. When we talk about software testability, we're really defining the ease with which software can be made to demonstrate its faults. Specifically through execution-based testing. It's not just about finding a bug eventually, it's more the probability that if a fault does exist, the system will fail on its very next test execution. And crucially, that we can immediately locate the cause.
So we're not just trying to reveal a fault. We want to make it easy to replicate that fault and then, pinpoint its root cause. That ease of replication, that's where the architecture really steps in, isn't it?
Precisely. Think of the simple model of testing input goes into a program, something comes out, the output. But to judge correctness, you need the oracle.
The oracle.
Yeah, this is the agent, maybe a human, maybe automated software that compares the output and, importantly, the internal state against what was expected.
The judge of truth, basically.
Yeah.
And the key ability the architecture must provide is that control and observation of the program's internal state, so the oracle actually has something concrete to judge.
Exactly, and that capability. It's usually provided by something called a test harness. This is specialized software, sometimes hardware, designed specifically to control the execution environment, feed in the necessary inputs, help run the test procedures, and critically record those inputs, outputs, and internal state changes.
Okay, let's unpack this idea of architectural control. Maybe with perhaps the most famous, definitely advanced, real-world example of testability. Netflix's Simian Army. This isn't just about unit tests. This is architecting for resilience in a massive adaptive system where, complex behaviors are constantly emerging.
Netflix has an extreme requirement for high availability, right? They host their massive streaming services on the Amazon EC2 cloud. And they realized pretty early on that failures were just inevitable. So instead of trying to prevent every single one, they architected their system to expect them. They used the Simian Army to actively ensure resilience.
It started with the original Chaos Monkey, didn't it? The idea was kind of beautifully simple, just randomly kill processes in the live running system.
Right.
If the system was architected correctly, the rest of the ecosystem wouldn't suffer serious degradation. It's like forced exposure therapy for distributed systems.
And this concept, it evolved into a whole army, really illustrating how testability can be targeted at specific, complex failure modes.
Let's run through some of those specialized operators. There was the Latency Monkey.
Yeah, that one induced artificial network delays. It simulated service degradation, basically checking if upstream services, the ones depending on that now slow service, responded gracefully.
Okay. And then there was a kind of cleanup crew, the Conformity Monkey.
That's right. It shut down instances that didn't follow cloud best practices, like instances not belonging to an auto-scaling group, just enforcing the rules.
And they had their own version of internal diagnostics, too.
They did. The Dr. Monkey used health checks and other external signs like CPU load to detect and, remove instances that seemed unhealthy. And the Janitor Monkey was there to clean up clutter, getting rid of unused, orphaned resources in their cloud environment.
We also saw security and even localization get their own specialized testing agents.
Absolutely. Security Monkey was kind of an extension of conformity checks, but focused on finding security vulnerabilities, improperly configured access groups, making sure essential SSL or DRM certificates were valid, things like that.
And the really fascinating one, the 1018 Monkey, named for the character, counts in localization, L10N, and internationalization, I18N.
Exactly. It was designed specifically to detect configuration or runtime problems in systems serving their global multilingual audience, making sure things looked right everywhere.
So this whole approach highlights a critical architectural strategy. They actively used fault injection, controlled placement of faults into a running system alongside specialized monitoring.
Right. It tells us that if your architectural analysis points to certain faults as being the most severe or most common, you really have to build testability tools right into the system structure to prioritize finding those specific faults.
The Simian Army really shows the extreme of what's possible in testing live, complex systems. But, okay, how do we formally ask for this kind of capability from our architects? We need some kind of structure, right?
We do, and that's where the Testability General Scenario comes in. It's a framework that helps us characterize precisely what we need from a system's testability. It breaks the requirement down into 6 key elements.
Elements, okay.
We start with the source. Who's running the test? Is it a developer doing unit testing? An integration team? System testers? Maybe even end users? And is it automated or manual?
That leads naturally to the stimulus. Why are we running the test? Is it just to validate a core function works? Or check if a quality goal like latency is being met? Or maybe we're actively hunting for new emerging security threats?
Next is the environment. When does this testing happen? Is it immediately after a small coding increment is done, during subsystem integration, or maybe after the whole system is deployed and running live, like that Chaos Monkey scenario we just discussed?
And the artifacts define what is actually under the microscope. Is it a single unit of code, a component, a service, an entire subsystem? Sometimes, believe it or not, we even need to test the robustness of the test infrastructure itself.
Then there's the response. This outlines what the system must enable for the tester. This is really the heart of control and observation we talked about earlier. Things like executing a test suite and capturing the results, being able to control and monitor the internal state of the system, or capturing the exact sequence of activity that led to a specific fault.
And finally, we have the response measures. This turns a requirement into something, well, measurable. How is testability actually measured?
Good question. It could be by the effort, maybe time or person hours required to find a fault, or the time it takes to perform a set of tests, or the effort needed just to get the system into that tricky specific state required for a particular test. Or maybe it's measured by the overall reduction in risk exposure achieved through the testing.
Okay, so if we put all that together, you get a concrete scenario statement.
Exactly, something like this. The developer completes a code unit during development and performs a test sequence whose results are captured, and that gives 85% path coverage within 30 minutes. See? That single statement incorporates the source, stimulus, environment, artifact, response, and the measure.
Perfect. That moves us nicely from the what the requirements to the how, the implementation strategy. What are the specific architectural tactics we use to actually achieve this testability? The first major category seems to be about giving the tester, well, superpowers over the system state. Control and observe system state.
That's a good way to put it. And the first tactic here is creating specialized interfaces. These are basically routines, methods added to components only for testing purposes.
Like what specifically?
Think of simple set or get methods for key internal variables that aren't normally exposed, or maybe report methods to quickly dump the entire state of an object, or reset methods to put a component back into a known specified configuration instantly. Even methods to turn on really verbose logging or instrumentation just for the test run.
But hold on. If we're adding code specifically for testing, say, those set and report methods, what happens? Do we leave them in the production environment? Because that feels risky. Or if we take them out for performance or security, how do we know the code we tested is actually the same code we're releasing? That sounds like a potential architectural loophole.
It is. It's the inherent trade-off, really. Ideally, you'd want to separate that specialized code, maybe using preprocessor macros or perhaps dependency injection techniques, so it's literally not compiled into the released version.
Okay.
However, in some domains, like safety-critical or high-security systems, that risk of non-conformance between the tested code and the released code might be completely unacceptable, so it forces a difficult architectural choice sometimes.
Understood. So it's a balancing act. What's next in the control and observe toolkit?
Record playback. Faults in complex systems, especially distributed ones, can be notoriously difficult to reproduce. This tactic involves capturing the specific state and the exact sequence of events as they cross an interface.
So if a fault occurs,
If a fault occurs, you can then replay that exact sequence using the recorded state data to rapidly and reliably recreate the failure condition for debugging. Huge time saver.
and related to that, I imagine, is localized state storage.
Exactly. You can't easily record and play back a system's state if it's scattered across 50 different components in unpredictable ways. By externalizing system state and maybe consolidating it, often using a dedicated state machine object or something similar, you make the state much more amenable to both examination and manipulation. It lets the tester start the system in almost any arbitrary configuration needed for a test.
And you also need to control the data flowing through, right?
Absolutely. Abstract data sources is the tactic here. It means architecting interfaces so that we can easily swap out production data sources, like the real live database, with test-specific data sources. That might be a dedicated test database or even just simple flat files. The key is doing it without forcing changes to the core functional code itself.
This seems to lead naturally into the sandbox tactic.
It does. The sandbox isolates a system instance from the real world. It lets you experiment without permanent consequences. And probably the most powerful example of this is virtualizing resources.
Like the system clock.
Precisely. We can't control the actual flow of real time, obviously. So virtualizing resources like the system clock becomes essential for certain kinds of testing.
Right, you could run the virtual clock much faster than wall clock time to hit specific critical time boundaries. Like testing what happens exactly at midnight when maybe all your financial data structures are supposed to cycle over. You could test that in minutes instead of waiting hours. That ability to control time seems fundamental for testing any time-sensitive system.
It really is. And simpler forms of virtualization, things like stubs, mocks, dependency injection frameworks, they are also crucial tools that fall under this umbrella.
Okay, what else under control and observe?
One more key tactic: executable assertions. These are typically hand-coded assertions checks placed directly in the code. They might be preconditions, what must be true before a method runs, post-conditions, what must be true after, or class-level invariants, what must always be true for an object.
So they effectively embed the test oracle or part of it right into the code itself.
Exactly. They check that data values satisfy specific constraints and will flag a failure the very moment the system enters an invalid state, often much earlier than a traditional test might catch it.
Okay, that covers controlling and observing state. That brings us to the second major category of tactics, limiting complexity. Once we can control the state, the next battle is complexity itself. Because, well, complex software just has an enormous operating state space, making fault recreation exponentially harder.
Yeah, complexity is a killer for testability. The first tactic here is limit structural complexity. This aligns heavily with goals for modifiability, which we've discussed before, but here we're looking at it specifically through the lens of testing effort. Well, we aim to avoid or resolve things like cyclic dependencies between components. We want to reduce coupling generally. This means ensuring each component is cohesive, focused on a single responsibility.
Okay, but how does that specifically help testing effort rather than just, say, long-term maintenance?
Think about it. If you have high coupling, where component A relies heavily on B, which relies on C, which maybe even relies back on A, then testing component, A requires setting up this whole tangled web of B and C, maybe even the whole system.
Right, a huge amount of setup.
Exactly. If you reduce that coupling, make A more independent, you can often test A in isolation just by using simple mocks or stugs for B and C. That dramatically simplifies the test setup and reduces the overall test time.
Makes sense. And for object-oriented systems.
For IUO systems, this also translates to practical advice like limiting the depth of inheritance trees, limiting the sheer number of classes derived from a base class, and maybe being cautious about excessive polymorphism, which can make tracing execution flow harder.
I remember seeing a metric mentioned for this in the source material, the responsive class. Can you clarify what that measures again?
Certainly. The responsive class, or ROC, is a measure that's been empirically correlated with testability effort. It's essentially a count of the methods within a specific class, plus the methods of all other classes that are directly invoked by the methods of that first class.
Oh, okay.
If that number gets really high, it's a strong indicator that the class is highly coupled and probably quite complex internally, making it extremely difficult and time-consuming to test exhaustively.
Got it. So keep that ROC number down. What's the second complexity tactic?
The second one is limit nondeterminism. This means actively finding and, where possible, weeding out sources of unpredictable behavior. The classic example is unconstrained parallelism in multi-threaded systems.
Ah, yes, the Heisenbugs.
Exactly. Trying to debug a fault that only happens one time in a million due to some obscure thread race condition is, well, the ultimate testing nightmare. If some non-determinism is absolutely unavoidable for functional reasons, then we have to rely heavily on our previously discussed tactic, record playback, to manage that complexity by capturing the unpredictable sequence when it does cause a failure.
Okay, that covers the tactics. Now to wrap up our architectural toolbox for testability, let's look at 3 specific architectural patterns. that seem fundamentally designed to help decouple the test-specific code and configurations from the core business functionality.
Good idea. First up is the very powerful Dependency Injection, DI pattern. This uses the principle often called inversion of control. Instead of a client component creating its own dependencies, say directly instantiating or connecting to a production database service, those dependencies are provided or injected from outside, usually by some kind of external framework or injector.
So the benefit for testing is huge then, right? Since the client doesn't hard-code its dependency, you just tell the injector to give it a mock database instance instead of the real one during tests.
Precisely. The client code can be written without ever needing to know how it will be tested or what concrete implementation it's talking to. It receives the test dependency seamlessly. The main trade-off, though, is that implementing DI does add some initial structural complexity to the system setup. And occasionally, the indirection can introduce slight overhead that might make runtime performance a tiny bit less predictable.
Okay, fair enough. Next up, the strategy pattern. This one allows a class's specific behavior, its algorithm basically, to be changed dynamically at runtime, often based on context.
Yeah, this is great for both simplification and testing. It lets you swap out, say, a complex production algorithm, maybe a financial calculation for a test version. That test version could return known fixed values, or maybe it includes extra sanity checks and logging output specifically for the test run.
So it simplifies the core class.
It does. It helps prevent the core class from becoming a huge monolithic switch statement or a series of complex if-else blocks trying to handle multiple algorithmic variations internally.
Okay, if the strategy pattern is about swapping out core functional behavior, how does that differ from the third pattern, the intercepting filter pattern? What problem does the filter solve that strategy doesn't seem to address?
That's a great distinction to make. The strategy pattern typically handles variations in the core functionality or algorithm. The intercepting filter pattern, on the other hand, is usually aimed at handling cross-cutting concerns.
Cross-cutting concerns like,
Things like logging, authentication, data validation, compression, encryption, stuff that needs to happen across many different requests or components. This pattern injects pre-processing and/or post-processing filters into the request or response stream, usually between the client and the actual target service.
so you could insert a specific testing filter, say, one that checks if an incoming authentication token is valid and maybe logs its expiry time without ever having to touch the core service logic itself.
Correct. This externalization makes the core service classes simpler because they don't have to worry about these tangential concerns. It also reduces code duplication and promotes reuse of those filter components. The major trade-off here, though, can be performance.
Oh, so.
Well, if you're passing very large amounts of data through the stream, and every single filter in the chain has to make a complete pass over that entire chunk of data, you can potentially introduce significant inefficiency and add noticeable latency to the request processing.
That makes sense. Okay, that's a really comprehensive look at how architectural foresight can translate into, well, fewer headaches and lower costs down the line during testing. So, to quickly recap for you listening, we define testability as the ease of making software reveal its faults cheaply and quickly. We explored Netflix's extreme model of resilience testing via the Simian Army. We looked at structuring testability requirements using the Testability General Scenario framework. And then we outlined those essential architectural tactics grouped into control and observe system state and limit complexity before finally examining specific patterns like dependency injection, strategy, and intercepting filter that help us implement those tactics cleanly.
And making those key architectural choices early on, whether it's consciously limiting coupling through good structural discipline or deciding to adopt a framework that supports dependency injection, that's what translates directly into saving significant development effort, time, and ultimately maintenance costs later in the project lifecycle. Testability, you could argue, is truly the architect's most valuable budget protector.
It certainly sounds like it. And this brings us to a fascinating final thought for you to maybe chew on after this. A system that is designed to be testable is designed to easily give up its faults, to make them visible so you can find them. But fault tolerance, another critical quality attribute, is often about designing systems that jealously hide their faults, that contain them so the user never even sees a failure. So the question is, can an architecture be designed to be both highly testable and highly fault tolerant, or are these two fundamental design goals ultimately incompatible at some level?
That tension, the push and pull between revealing faults to the tester and hiding them from the end user, that really is the ultimate balancing act for almost any system architect. Thank you for joining us on this deep dive today.